There is a place in the universe where the laws of physics, as we understand them, quietly stop working. Not break, not bend, stop. It is not a place on any map. It has no surface you could stand on, no wall you could touch, no color you could see. It does not glow. It does not announce itself. From a distance, in the right conditions, it looks like nothing at all. A circle of absolute darkness surrounded by a halo of distorted light. A hole in the fabric of the visible cosmos where everything that falls in, every photon, every atom, every memory stored in the atoms of a human body, disappears from the observable universe forever. We call the boundary of that place the event horizon. And what happens there, what physics does, what time does, what space itself does at the edge of a black hole, is among the most disorienting, counterintuitive, and genuinely terrifying things that mathematics has ever described. The terrifying part is not the destruction. The terrifying part is the silence. The event horizon does not scream. It does not vibrate or crackle or burn. It sits in space like a held breath, perfectly still, perfectly patient. And from the outside, you cannot see a single thing falling in. Not the light, not the matter, not the last moment of anything that crossed it. The universe keeps its secrets behind that boundary with a thoroughness that no other phenomenon in nature can match. If you want to understand the cosmos at its most extreme, the places where gravity wins completely, where time runs at a different rate, where the geometry of space itself becomes a one-way door, then that is where the conversation begins and ends. At the event horizon, at the place where everything we know runs out. Chapter 1. The idea that should not have worked. The story of the black hole begins not with a telescope, not with an observation, not with anything seen in the sky at all. It begins with an equation written in the trenches of the First World War by a man dying of a skin disease contracted on the Eastern Front who had nothing to do but think. His name was Karl Schwarzschild. He was a German physicist and astronomer serving as a lieutenant in the German artillery on the Russian front in late 1915. While calculating trajectories for artillery shells, he found time to read a paper that Albert Einstein had just submitted to the Prussian Academy of Sciences. The paper described a new theory of gravity, not Newton's inverse square law, but a fundamentally different description of how mass curves the fabric of space-time itself. Einstein had spent 10 years arriving at this theory. He had called it the general theory of relativity. It replaced Newton's concept of gravity as a force acting across empty space with something stranger and more beautiful. The idea that mass and energy warp the geometry of four-dimensional space-time, and that what we call gravity is simply the tendency of objects to follow the straightest possible paths through that curved geometry. The mathematics was formidable. Einstein himself had not found exact solutions to his own field equations. He believed at the time that exact solutions might be impossible to derive. Schwarzschild derived one within 2 months. He sent it to Einstein from the front, along with a note apologizing for the rough conditions under which the solution had been produced. Einstein read it and replied that he had not expected the exact solution to be derivable so simply. He presented Schwarzschild's paper to the Prussian Academy in January 1916. Schwarzschild died 4 months later. The solution he left behind described the geometry of space-time around a perfectly spherical, non-rotating, non-charged mass. It was an idealization, but it was exact. And buried within it was something that Schwarzschild himself noted, but which neither he nor Einstein fully reckoned with. There was a radius, a specific distance from the center of any mass, at which the solution produced what appeared to be a mathematical singularity. The equations went to infinity. They broke down. They stopped making physical sense. Schwarzschild called it the Schwarzschild radius. For the Sun, it works out to approximately 3 kilometers. For the Earth, it is about 9 millimeters. For a person of average mass, it is somewhere in the neighborhood of 10 to the negative 25 meters, far smaller than an atomic nucleus. The conventional wisdom at the time was that the Ozai singularity was a mathematical artifact, a ghost in the equations that had no physical reality. For any real object, the Sun, a star, a planet, the Schwarzschild radius was buried deep inside the object itself, in a region where the vacuum solution did not apply because the matter of the object was still present. The question no one wanted to take seriously was this: what if you could compress an object until its entire mass lay inside its own Schwarzschild radius? What would happen then? The answer, as subsequent decades of increasingly reluctant physics would reveal, was that a point of no return would form in space. A boundary. A sphere of radius equal to the Schwarzschild radius surrounding the compressed mass. A surface from which nothing, not matter, not light, not information of any kind, could escape back to the outside universe. A one-way membrane in the fabric of space-time, the event horizon. Einstein himself did not believe this could actually happen in nature. In a 1939 paper, he argued that the orbital mechanics of stellar material would prevent any star from collapsing to the Schwarzschild radius. He was wrong, though not about the orbital mechanics. What he missed was a subtler and more powerful argument that arrived that same year from a physicist named J. Robert Oppenheimer. Oppenheimer and his student Hartland Snyder published a calculation in September 1939. The same month, Germany invaded Poland. The same month, the world stopped paying attention to abstract physics, showing that a sufficiently massive star, once it exhausted its nuclear fuel, had no mechanism capable of halting its gravitational collapse. The outward pressure of radiation and hot gas that held the star up against its own gravity would vanish when the fuel ran out, and nothing else in known physics could resist the inward pull. The collapse would be total, complete, and unstoppable. The star would compress past the Schwarzschild radius. An event horizon would form. The result was too strange to be accepted quickly. Most physicists either ignored it or looked for reasons to disbelieve it. It would take 3 more decades and the discovery of pulsars, quasars, and neutron stars before the physics community gradually, grudgingly, accepted that black holes were not a mathematical curiosity but a physical reality. But the event horizon was there from the beginning, sitting in Schwarzschild's equations from 1916, waiting to be taken seriously. Chapter 2. The Geometry of No Return. To understand what the event horizon actually is, you need to understand something about how general relativity describes gravity. In Newton's universe, gravity is a force. Mass pulls on mass across empty space. You can resist this force with thrust, with orbital velocity, with another force pushing back. If you are falling toward a massive object, you can always, in principle, fire your engines and escape, as long as you have enough fuel and the engine is powerful enough. In Einstein's universe, gravity is not a force at all. It is geometry. Mass curves space-time, and objects move along the straightest possible paths through that curved geometry. What looks like falling is simply the natural path of an object through warped space and time. You are not being pulled toward the Earth. You are following the geometry of space-time in Earth's neighborhood, and that geometry happens to curve toward Earth. This distinction sounds like philosophy until you reach extreme cases, and black holes are the most extreme case imaginable. Near a black hole, the curvature of space-time does not just deflect paths. At the event horizon, it does something more fundamental. It redirects all future pointing paths, every possible trajectory you could take through space-time, toward the interior of the black hole. Think of it this way. In ordinary space-time, if you shine a flashlight in any direction, the beam travels outward, away from you, toward the future and toward larger distances from any gravitational source. This is what it means for space-time to be relatively flat. The future is, in a sense, open. You can go many directions. As you approach a black hole, space-time curves more severely. The future-pointing directions of space-time, the directions in which time and space allow you to travel, begin to tilt toward the black hole. You can still escape if you fire your engines, but you need more and more thrust to do so as you get closer. At the event horizon, the tilting reaches its limit. The entire future light cone, the complete set of all possible directions any signal, any particle, anything could travel, points entirely inward, not mostly inward. Entirely. There is no future pointing direction at the event horizon that leads outward. Time itself, in a sense, points toward the singularity. This is not a wall. There is no wall. The event horizon is not a physical surface you would crash into or bounce off of. If you were falling through it, you would feel nothing. You would not know in the moment of crossing that you had crossed anything at all. The local physics at the event horizon, for a freely falling observer, looks completely ordinary. There is no flash of light, no shockwave, no physical sensation marking the moment of no return. The point of no return has already been passed before you knew it was there. This is one of the most deeply unsettling aspects of the event horizon. It is invisible from the inside. Once you are inside, there is no looking back. Not because something blocks your vision, because the geometry of space-time inside the event horizon does not contain any outward pointing directions. Light emitted from inside a black hole does not travel outward and get absorbed by the event horizon. It travels toward the singularity, because that is the only direction the future exists. The event horizon is the surface where time, as experienced by an external observer watching you fall in, effectively stops. But the physics at the horizon, experienced by the falling observer, is perfectly normal. This dichotomy, one event appearing completely different to two different observers, is the heart of what makes black hole physics so philosophically and mathematically challenging. Chapter 3. Time at the Edge of Forever. Of all the strange things the event horizon does, what it does to time is perhaps the most disturbing. General relativity predicts that time runs at different rates in different gravitational environments. This is not an approximation or a philosophical statement. It is a physical, measurable fact, confirmed to extraordinary precision by atomic clocks placed at different altitudes, by corrections required by the GPS satellite system, by observations of neutron stars, pulsars, and white dwarfs. Clocks closer to a massive object run slower than clocks farther away. The deeper you are in a gravitational well, the slower time passes for you relative to someone outside that well. This effect is called gravitational time dilation. Near the surface of the Earth, it is tiny. GPS satellites must account for it precisely. Their clocks run slightly faster than Earth surface clocks, due to weaker gravity and slightly slower due to their orbital velocity. The net effect is a difference of approximately 38 microseconds per day, small but large enough to cause GPS systems to accumulate significant errors if left uncorrected. Near a black hole, the effect is not tiny. As you approach the event horizon of a black hole, the gravitational time dilation becomes more and more extreme. An observer far from the black hole, watching you fall in, sees your clock running slower and slower. Your heartbeat, as observed from a safe distance, slows down. Your movements slow. The light you emit becomes redder, gravitationally redshifted, as it climbs out of the deepening gravitational well to reach the distant observer's eyes. At the event horizon, gravitational time dilation becomes infinite. An outside observer watching something fall into a black hole never sees it cross the event horizon. Not because the crossing doesn't happen, but because the light emitted at the moment of crossing takes, from the outside perspective, an infinite amount of time to travel outward. The falling object appears to slow asymptotically, its image growing redder and dimmer, fading toward invisibility over an exponentially increasing timescale. It never disappears in a single moment. It simply dims. It redshifts into the infrared, then the microwave, then below any wavelength an observer could detect. From the outside, the event horizon looks frozen. The last images of everything that ever fell in, infinitely redshifted and time-dilated, are encoded on its surface in a way that gradually fades to undetectability. Nothing appears to happen there. The surface appears static, cold and dark. But from the perspective of the object falling in, something very different is happening. The freely falling observer, in their own reference frame, experiences no infinite time dilation. They cross the event horizon in finite time. For a sufficiently large black hole, they may not even notice. They feel no special force, encounter no wall, hear no alarm. The crossing is silent and invisible. Only after the fact, if they could somehow calculate their trajectory, would they know they had passed a point of no return. This is the fundamental observer dependence of the event horizon. It is not a moment that both observers agree on. It is a feature of the global structure of space-time, detectable only to someone who can see the whole picture. The falling observer cannot, from inside, establish that they have crossed any meaningful boundary. The outside observer never sees the crossing happen at all. Two descriptions of the same event, neither wrong, neither complete. This is not a paradox in the sense of a logical contradiction. It is a genuine feature of how general relativity treats observers in different states of motion and different gravitational environments. But it is the kind of feature that makes the human mind want to push back, to demand that one description be the real one, to insist that there must be a single truth about when and whether the crossing happened. General relativity does not provide that comfort. The event horizon is, in some sense, different things to different observers, and both descriptions are correct. Chapter 4. Spaghettification and the singularity beyond. Past the event horizon, the physics of a black hole becomes something that current science cannot fully describe. The singularity at the center of a black hole, the point toward which all infalling matter inevitably travels, is not a physical object. It is a boundary of the mathematical description, a place where the equations of general relativity produce infinite density, infinite curvature, infinite space-time distortion, where the theory breaks down and stops producing meaningful predictions. General relativity, the same theory that so precisely described the event horizon and gravitational time dilation, fails at the singularity. The theory itself signals its own incompleteness by producing infinities. Physicists have known since the 1960s, following the work of Roger Penrose and Stephen Hawking on singularity theorems, that these infinities are not artifacts to be removed by better mathematics. They are predictions of the theory itself. The singularity at the center of a black hole is where a complete theory of quantum gravity, a theory that does not yet exist, would need to take over from general relativity. But before reaching the singularity, something happens that is both more immediate and more visceral. And it demonstrates in stark physical terms what it actually means for space-time curvature to become extreme. Tidal forces. Tidal forces are the differential gravitational effects experienced by an extended object, an object with size, falling through a region of varying gravitational field. The side of the object closer to the gravitational source feels a stronger pull than the side farther away. The result is a stretching along the radial direction and a compression perpendicular to it. You experience a tiny version of this on Earth. The side of your body facing the Earth's center is pulled very slightly harder than the side facing away. But the difference in gravitational field strength across the length of a human body at Earth's surface is negligibly small. No biological system is sensitive to it. Near a black hole, tidal forces become lethal. The rate at which they become lethal depends critically on the mass of the black hole. For a stellar mass black hole, the kind formed by the collapse of a single massive star, with a mass of a few to a few dozen times the mass of the Sun. The Schwarzschild radius is only a few to a few tens of kilometers. The gradient of gravity across the event horizon is steep. As a human body approaches such a horizon, the tidal forces become enormous long before the event horizon is reached. The feet, if you are falling feet first, are pulled much harder than the head. The body is stretched radially and compressed laterally. First, the discomfort becomes severe. Then the structural integrity of bone and tissue gives way. The body is elongated into a thin stream of particles, each particle following its own geodesic through the increasingly curved space-time, the stream getting thinner and longer as the curvature increases. This process has a name: spaghettification. It is not a metaphor. It is an accurate description of what the physics predicts. But for a supermassive black hole, the kind that sits at the center of a galaxy with a mass millions or billions of times that of the Sun, the Schwarzschild radius is enormous, millions to billions of kilometers. The curvature at the event horizon of such a black hole is gentler because the horizon is so far from the singularity in spatial terms. The tidal forces at the event horizon itself may be mild enough that a human body could cross without immediate physical disruption. At the center of our own Milky Way sits a black hole called Sagittarius, a star, with a mass of approximately 4 million solar masses. Its Schwarzschild radius is roughly 12 million kilometers, about 1/10 the distance from Earth to the Sun. At that event horizon, the tidal forces, while significant, would not immediately destroy a human body. The crossing itself would be survivable in the immediate physical sense. What would not be survivable is everything else. The radiation environment inside the accretion disk surrounding an active black hole. The trajectory toward the singularity, which from the inside becomes a matter of time rather than space. A future boundary that approaches no matter what direction you try to flee toward. And ultimately, whatever the singularity does to matter, which no current physics can predict. The Penrose singularity theorem, proven in 1965, established that once you are inside an event horizon, a singularity is in your future. Not in some spatial direction, in your future. You cannot avoid it by steering, by firing your engines, by choosing a different path. The geometry of space-time inside a black hole ensures that all future-directed paths lead to the singularity. It is, in the most literal possible sense, unavoidable. It is where time ends. What that ending looks like, what happens to the matter and information that reaches the singularity, these are questions that physics cannot currently answer. They are the questions that a theory of quantum gravity would need to address, and we do not have a theory of quantum gravity. Chapter 5. The Information Paradox. Here is a question that sounds simple. If you throw a book into a black hole, what happens to the information in the book? The letters, the words, the sentences, the meaning. All of that is physically encoded in the arrangement of atoms in the paper and ink. When those atoms fall through the event horizon, they take the information with them. The book disappears. The information disappears. But in quantum mechanics, information cannot be destroyed. This is not a philosophical preference. It is one of the foundational mathematical requirements of quantum theory. The principle is called unitarity. The complete information about the initial state of any physical system is always preserved in its final state, even if transformed beyond recognition. Burning a book scrambles the information into heat and gases and ash, but in principle, if you could track every particle and every photon produced by the fire, you could reconstruct the original text. The information is not destroyed, it is hidden. A black hole on the surface seems to violate this. Matter falls in. The event horizon prevents anything from coming back out. The information in the matter seems to disappear completely from the observable universe. This is the black hole information paradox, and for nearly 50 years, it has been one of the deepest unsolved problems in theoretical physics. It was Stephen Hawking who made the paradox sharp and unavoidable. In 1974, Hawking published a calculation that stunned the physics community. Using quantum field theory applied in the curved space-time near a black hole, he showed that black holes are not perfectly black. They radiate. Not from their interiors, not by ejecting matter that has already crossed the event horizon, but from the region just outside the event horizon through a quantum mechanical process that has no classical counterpart. The mechanism involves the quantum vacuum. In quantum field theory, empty space is not truly empty. It seethes with virtual pairs of particles and antiparticles, constantly being created and annihilated. Near the event horizon of a black hole, a pair can be created in which one particle falls inside the horizon while the other escapes. The escaping particle carries energy away from the black hole. The infalling particle carrying negative energy reduces the black hole's mass. Over time, the black hole radiates away its mass as a thermal spectrum of radiation, what is now called Hawking radiation. The temperature of this radiation is inversely proportional to the mass of the black hole. For stellar mass black holes, it is fantastically cold. Far colder than the cosmic microwave background, meaning such black holes are currently absorbing more radiation than they emit. But as a black hole evaporates, it gets smaller, hotter, and radiates more intensely, until in its final moments it radiates explosively, then vanishes. The crisis this creates for the information paradox is severe. Hawking's calculation showed that the radiation produced by this process is purely thermal. It carries no information about what fell into the black hole. It is the same regardless of whether you started with a library of books, a collection of photographs, or a uniform cloud of hydrogen gas. Throw anything into the black hole, and the Hawking radiation that eventually emerges is identical. The information is gone. If the radiation truly carries no information, then quantum mechanics is violated. Unitarity breaks down. The fundamental structure of quantum theory is undermined by the existence of black holes. This is the information paradox in its sharpest form. General relativity and quantum mechanics, the two most successful and precisely tested theories in the history of physics, make contradictory predictions about what happens to information near a black hole. The debate over the resolution of this paradox has consumed decades of theoretical effort. Some of the most brilliant physicists alive have worked on it. Hawking himself initially argued that information was genuinely destroyed, that black holes represented a fundamental breakdown of quantum mechanics. In 2004, he publicly reversed his position, conceding that information is most likely preserved and escapes in the Hawking radiation, encoded in subtle quantum correlations that his original calculation had missed. But the question of exactly how the information escapes, how the correlations work, what physical mechanism encodes the information of the infalling matter into the outgoing radiation remains unsolved. Various proposals have been advanced, each carrying serious conceptual difficulties. One of the most dramatic is the firewall hypothesis, proposed in 2012 by Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully. Their argument, now known as the AMPS firewall, suggests that in order to preserve quantum mechanical unitarity, the infalling observer must not experience an unremarkable crossing of the event horizon. Instead, the event horizon must be surrounded by a wall of high-energy radiation, a firewall that incinerates anything approaching it. The firewall resolves the information paradox at the cost of violating the equivalence principle, one of the foundational postulates of general relativity, which states that a freely falling observer in a gravitational field should not be able to detect any locally unusual physics. If a firewall exists, freely falling observers are burned before they cross the horizon. The event horizon becomes a physical surface after all, not just a geometric boundary. But this creates its own paradox, because the physics that predicts the firewall depends on the existence of long-range quantum correlations, entanglement between Hawking radiation particles emitted at different times, that seem to contradict the structure of the quantum vacuum near the horizon. The firewall debate is ongoing. It has produced, in the decades since AMPS, some of the most creative theoretical work in physics since the original development of quantum mechanics. It has connected black hole physics to information theory, to quantum computing, to holography, and to ideas about the fundamental structure of space-time itself. It has not been resolved. The event horizon remains, at its most fundamental level, an unsolved problem. Not just an interesting place in space-time, but a boundary at which two of our most powerful theories of nature come into direct and irreconcilable conflict. Chapter 6. The A. Schwarzschild. Radius and the varieties of black holes. Not all black holes are the same, and the differences between them are not merely differences of scale. They involve different formation mechanisms, different surrounding environments, and subtly different physics at the event horizon. Stellar mass black holes are the most common variety, or at least the most commonly understood. They form when a massive star, with a mass roughly 8 or more times that of the Sun, exhausts its nuclear fuel and undergoes core collapse. The core, stripped of the outward pressure that supported it, collapses under its own gravity in less than a second. If the core mass exceeds approximately 3 solar masses, the Tolman-Oppenheimer-Volkoff limit for neutron star stability, not even the quantum degeneracy pressure of tightly packed neutrons can halt the collapse. A black hole forms. The outer layers of the star, lacking support from the now collapsed core, fall inward and then rebound in a catastrophic explosion, a supernova. For a fraction of a second, the exploding star outshines all several 100 billion stars in its host galaxy combined. And at the center, invisible and silent, a new black hole has been born. Stellar mass black holes range from a few to perhaps a few hundred solar masses. Their event horizons range from a few kilometers to perhaps hundreds of kilometers in radius. In the Milky Way alone, estimates suggest there may be hundreds of millions to a billion such objects. They are far too small and dark to see directly. We detect them through their gravitational influence on companion stars in binary systems, through the X-rays emitted by material spiraling into them from a stellar companion, and now directly through the gravitational waves emitted when two black holes merge. The gravitational wave detection of two merging black holes, announced by LIGO on February 11, 2016, almost exactly 100 years after Schwarzschild derived his solution, was the first direct observation of a black hole. What LIGO detected was the space-time distortion created by two black holes, each roughly 30 solar masses, spiraling together and merging in a fraction of a second, releasing energy equivalent to 3 solar masses in the form of gravitational waves. The signal lasted less than a second. The entire violent merger, the collision of two event horizons, was encoded in a microsecond wobble in the arms of LIGO's interferometer. Supermassive black holes are a different category entirely. They sit at the centers of most large galaxies, including our own. Their masses range from millions to tens of billions of solar masses. Their event horizons range from the size of the inner solar system to the size of the outer solar system. They are not formed by any single stellar collapse. Their formation mechanisms remain one of the open questions in astrophysics. They may have formed from the direct collapse of massive gas clouds in the early universe, from the runaway merging of stellar mass black holes in dense early star clusters, from some combination of processes that we have not yet fully characterized. What they do is clear, even if how they got there is not. They exert gravitational influence over their entire host galaxies. When material falls into them through an accretion disk, a vast, swirling disk of gas and dust heated by friction and compression, they become quasars, the most luminous sustained objects in the universe. A quasar can outshine its entire host galaxy of hundreds of billions of stars by a factor of 100 or more. All of that energy comes from the conversion of gravitational potential energy into heat and radiation as matter spirals down toward the event horizon. The first image of a black hole's shadow, the dark region silhouetted against the glow of the accretion disk, was produced by the Event Horizon Telescope collaboration and released on April 10, 2019. The target was M87 star, the supermassive black hole at the center of the galaxy Messier 87, 55 million light-years away, with a mass of approximately 6.5 billion solar masses. Its event horizon spans roughly 38 billion kilometers, larger than our entire solar system. The image showed exactly what general relativity predicted: a bright ring of radiation bent by the extreme gravity surrounding a dark central region. The shadow of the event horizon rendered visible by the glow of the infalling matter around it. A second image followed in 2022. Sagittarius, a star, the black hole at the center of our own galaxy, 4 million solar masses and 26,000 light-years away. Its event horizon, 12 million kilometers across, was imaged in the same way. A ring of bent light surrounding a circle of darkness. The object that Karl Schwarzschild's equations had implied in 1916, that Oppenheimer and Snyder had predicted in 1939, that physicists had debated for decades, stared back from a telescope array spanning the entire Earth. There is also, between these two extremes, a category of intermediate mass black holes, with masses in the range of hundreds to hundreds of thousands of solar masses. These are less well understood, harder to observe, and their formation mechanisms are debated. But evidence for their existence has accumulated over the past decade from various observational signatures, including the unusual properties of certain star clusters and the gravitational wave signals from unexpectedly massive merger events. Each type of black hole has an event horizon. Each horizon is defined by the Schwarzschild radius, or, for rotating black holes, by the more complex geometry described by the Kerr metric. But the physics at the horizon differs in its experiential consequences depending on the black hole's mass, as we have already discussed. What does not differ is the fundamental nature of the boundary itself. What does not differ is the irreversibility. Chapter 7. The rotating black hole and the ergosphere. The black holes that exist in nature are almost certainly not the perfectly static, non-rotating variety described by the Schwarzschild solution. Stars rotate. When they collapse, their rotation is amplified the way a spinning ice skater spins faster when they pull in their arms. Black holes born from stellar collapse are expected to be spinning rapidly, often close to the maximum physically allowed rotation rate. A rotating black hole is described by a different mathematical solution, the Kerr metric, derived by Roy Kerr in 1963. The Kerr solution is more complex than the Schwarzschild solution, and the geometry it describes is richer and stranger. A rotating black hole has two important surfaces rather than one. The first is the event horizon, which still exists and functions as a one-way membrane in the same fundamental way as the Schwarzschild event horizon. Once inside it, nothing returns. The second surface is outside the event horizon. It is called the ergosphere, and it is genuinely extraordinary. The ergosphere is a region of space-time surrounding a rotating black hole in which it is impossible for any physical object to remain stationary relative to the distant stars. Not difficult. Impossible. The rotation of the black hole drags space-time itself around with it, a phenomenon called frame dragging. Inside the ergosphere, space-time is being dragged in the direction of the black hole's rotation faster than light can travel. Because nothing can travel faster than light, and because staying stationary would require doing exactly that, everything inside the ergosphere, no matter how hard its engines fire, is forced to co-rotate with the black hole. The ergosphere extends beyond the event horizon, which means it is possible to enter it, do work, and escape. This possibility leads to one of the most extraordinary predictions in classical general relativity. Roger Penrose proposed in 1969 that energy could be extracted from a rotating black hole using the ergosphere. A hypothetical process. The Penrose process involves sending an object into the ergosphere, splitting it into two pieces, allowing one piece to fall into the event horizon with negative energy, and allowing the other to escape with more energy than the original object possessed. The extra energy comes at the expense of the black hole's rotation. The hole slows down. The escaping object carries away more kinetic energy than was put in. This is not a perpetual motion machine. The black hole pays the energy cost by losing angular momentum. But it means that rotating black holes are, in principle, energy sources. Their rotational energy can be extracted. For a maximally rotating black hole, up to 29% of its total mass energy can be extracted through such processes. Astrophysicists believe that processes related to the Penrose mechanism, mediated not by physical objects splitting in the ergosphere, but by electromagnetic and plasma (EI) physics, may be responsible for the extraordinarily energetic jets observed shooting out from the poles of active galactic nuclei. These jets, streams of plasma accelerated to close to the speed of light and extending for thousands to millions of light years, carry enormous energy. The best supported model for their origin involves magnetic fields threading the ergosphere of a rapidly spinning supermassive black hole, extracting rotational energy and channeling it into the jet. The black hole's spin powers one of the most energetic phenomena in the observable universe. The Kerr geometry also contains another curious feature: closed time-like curves. Under certain conditions within the Kerr geometry, in the interior, past the inner horizon, the mathematics allows for paths through space-time that loop back on themselves. Paths that could, in principle, allow an observer to return to their own past. This is generally considered unphysical. Most physicists believe that some mechanism, quantum effects, instabilities of the inner horizon, the physics near the singularity, prevents closed time-like curves from actually existing in a real Kerr black hole. The chronology protection conjecture, proposed by Hawking, suggests that the laws of physics conspire to prevent the formation of closed time-like curves that could be used for time travel, even in situations like the Kerr geometry, where the classical mathematics seems to permit them. But the mathematics of the Kerr metric undeniably contains them. Chapter 8. Hawking radiation and the slow death of black holes. The discovery of Hawking radiation in 1974 was not an experimental result. It was a theoretical prediction derived by Stephen Hawking by applying the mathematics of quantum field theory to the curved space-time geometry near a black hole's event horizon. The core idea draws on the quantum mechanical description of the vacuum. In quantum field theory, the vacuum state is not empty. It is a seething foam of quantum fluctuations, pairs of virtual particles constantly emerging from nothing and annihilating back into nothing on timescales so short that they do not violate energy conservation in any detectable way. Normally, these fluctuations have no macroscopic effect. They are not real particles. They cannot be detected directly. They cancel themselves out in every observable process. Near the event horizon of a black hole, however, something different can happen. A virtual pair is created just outside the horizon. One particle is on a geodesic that takes it outside the horizon and away. The other is on a geodesic that takes it inside the horizon. They cannot annihilate. They are separated by the boundary before they have a chance to cancel. The outside particle, which was virtual, becomes real. A real particle propagating away from the black hole. It carries energy. Where does that energy come from? From the black hole itself, which loses mass in exact proportion to the energy of the emitted particle. The radiation that results is thermal. It has a blackbody spectrum characterized by a temperature inversely proportional to the black hole's mass. The Hawking temperature for a black hole of mass m is given by a simple formula involving Planck's constant, the speed of light, Boltzmann's constant, and Newton's gravitational constant. For a stellar mass black hole of 10 solar masses, this temperature is approximately 6 billionths of a Kelvin. A temperature so far below the cosmic microwave background temperature of 2.7 Kelvin that such a black hole absorbs vastly more radiation than it emits. It will gain mass for the next several trillion years before the universe cools enough for it to begin net evaporation. For a primordial black hole of asteroid mass, perhaps formed in the early universe, the Hawking temperature would be high enough to produce significant radiation today. For a black hole of about 10 to the 11th kilograms, the Hawking temperature puts the object on the verge of completing its evaporation right now with a final burst of high-energy radiation. Searches for such evaporating primordial black holes have so far produced no detections. The mathematics of Hawking radiation leads directly to one of the deepest ongoing puzzles in theoretical physics, the information paradox we discussed earlier. But it also implies something even more fundamental. It implies that all black holes, given infinite time, will eventually evaporate. The event horizon that appeared eternal, that swallowed matter and seemed to hold it forever, is not permanent. It is temporary. The black holes that exist today will persist for timescales that dwarf the current age of the universe by incomprehensible factors. A stellar mass black hole will evaporate in roughly 2 times 10 to the 67 years. The current age of the universe is approximately 14 billion years, roughly 10 to the 10 years. The evaporation time exceeds the age of the universe by 57 orders of magnitude. Supermassive black holes will persist for far longer still, but they will end. Given time, given incomprehensible quantities of time, far beyond the death of all stars, far beyond any organized structure in the cosmos, they will radiate away their mass. The last black hole in the universe will emit a final burst of Hawking radiation, and the event horizon will close. The trapped information, somehow encoded in the quantum correlations of the radiation, will have returned to the universe. What remains unknown is whether that return is truly complete, whether the information is truly preserved, whether the principle of unitarity survives. That is the information paradox in its most physical form. Not a philosophical question about what information is, but a concrete mathematical question about whether quantum mechanics works the same way near a black hole as everywhere else. The answer is not known. Chapter 9. What we have seen and what it confirms. For most of the 20th century, black holes were a theoretical prediction supported by indirect evidence. The physics community was confident they existed. The evidence from X-ray binaries, from quasars, from the dynamics of stars near galactic centers was overwhelming. But no one had ever seen one, not directly. That changed in 2015, 2019, and 2022. The gravitational wave detections by LIGO and Virgo, beginning with the announcement of GW 150914 in February 2016, provided the first direct observation of black holes in the act of merging. The signal matched the predictions of general relativity with extraordinary precision. The frequency and amplitude of the gravitational waves as the two black holes spiral together, the sharp chirp at the moment of merger, the ring down as the newly formed merged black hole settled into a final Kerr state, all of it fit the theoretical predictions as closely as anyone had dared hope. By the end of 2023, LIGO and Virgo had detected well over 100 gravitational wave events, the vast majority from merging black hole binaries. The database of black hole properties has expanded dramatically. Black holes of unexpected masses have been found. Black holes in the so-called mass gap between the expected maximum mass of neutron stars and the expected minimum mass of black holes from stellar collapse have been observed. The field has moved from theoretical confidence to quantitative astrophysics. The Event Horizon Telescope. Images of M87 star and Sagittarius. A star provided the first visual confirmation of the predicted event horizon structure. The bright ring of emission surrounding a dark central shadow, the ring's precise dimensions consistent with the black hole masses inferred from other measurements, the photon ring structure predicted by general relativity, all present in both images. The photon ring deserves special mention. Immediately outside the event horizon, photons can travel in unstable circular orbits, neither falling in nor escaping, but trapped momentarily in a precarious balance between gravity and centrifugal effect. This unstable photon sphere creates a sharp bright ring in the observed image, with additional subrings from photons that have orbited the black hole multiple times before escaping. The mathematical precision with which the images conform to the predictions of the Kerr metric for a rotating black hole represents one of the cleanest confirmations of strong field general relativity ever obtained. These observations confirm, to the extent that physical observation can confirm a theoretical framework, that black holes are real, that event horizons exist as physical structures in the universe, and that the predictions of general relativity in the extreme curvature regime are accurate. What they cannot observe is the event horizon from the inside. What they cannot resolve is the fate of the singularity, the mechanism of information preservation, the physics at the Planck scale where quantum gravity must become relevant. The images show the shadow of the horizon. They confirm that the geometry outside the horizon is exactly what Einstein's equations predict. They say nothing about what lies beyond. Chapter 10. The boundary of physics itself. Here is the honest summary of what physics knows and does not know about the event horizon. We know the event horizon is real. We know it is defined by the Schwarzschild radius for non-rotating black holes and by the Kerr geometry for rotating ones. We know that it functions as a one-way membrane. Nothing that crosses it can return to the exterior universe. We know that from the outside, an infalling observer appears to freeze at the horizon in a state of infinite time dilation and infinite redshift. We know that from the falling observer's perspective, the crossing is smooth and unremarkable for sufficiently large black holes. We know that tidal forces become lethal before the horizon for stellar mass black holes and may be mild at the horizon for supermassive ones. We know that a rotating black hole has an ergosphere outside the event horizon from which energy can be extracted. We know that quantum field theory in curved spacetime predicts Hawking radiation, a slow thermal evaporation of the black hole driven by quantum vacuum effects near the event horizon. We know that this prediction implies black holes have temperatures and entropies, a result so profound that it opened an entirely new field of research into the thermodynamics of spacetime. We know that the information paradox is real and unsolved. We know that quantum mechanics and general relativity make incompatible predictions about what happens to information at the event horizon, and that no completely satisfactory resolution exists. The firewall debate is ongoing. The question of how and whether unitarity is preserved remains open. We know that the singularity inside the event horizon represents the breakdown of general relativity, a boundary where the theory itself signals its own incompleteness, where a theory of quantum gravity would be necessary to say anything meaningful. We do not have a theory of quantum gravity. String theory, loop quantum gravity, and various other approaches have made progress towards such a theory. None has produced experimentally verified predictions that would allow physicists to declare the problem solved. The singularity remains, in the most literal sense, beyond the reach of current physics. The event horizon is the boundary not just of the interior of a black hole, but of what current physics can say. The mathematics of general relativity describes the exterior region with extraordinary precision, confirmed by observation and experiment. It describes the event horizon as a geometric structure in space-time, a feature of the global topology of the space-time manifold. It breaks down at the singularity. Quantum field theory, applied in the weak field regime near but outside the event horizon, produces Hawking radiation, a result of such mathematical elegance and physical consequence that most physicists accept it as almost certainly correct, even though it has never been directly observed. It breaks down in the strong field, high curvature regime near the singularity. The event horizon sits between these two domains. It is where the smooth classical geometry of general relativity begins to be corroded by quantum effects. Effects that become fully dominant only at the singularity, but whose precursors in the form of Hawking radiation and the information paradox are felt even at the comparatively gentle curvatures of the horizon itself. Every deep question about black holes, what happens to the singularity, whether information is preserved, whether firewalls exist, what quantum gravity looks like at the Planck scale, ultimately lives at or near the event horizon. The horizon is not just a physical boundary, it is an epistemological one. It is the edge of what we can currently say anything meaningful about. Chapter 11. The scale of the darkness. To make the event horizon feel real rather than abstract, it helps to bring the numbers out of the equations and into the world. At the center of the Milky Way, 26,000 light-years from Earth, lies Sagittarius, a star. Its mass is 4.1 million solar masses. Its Schwarzschild radius is approximately 12.4 million kilometers. If you placed the event horizon at Tiart, the center of our solar system, it would extend 8% of the way to the Sun. It is larger than the orbit of Mercury around a typical star. The space within it, the volume from which light cannot escape, encloses a region roughly 120 million kilometers across. Everything inside that sphere is gone from the observable universe. M87 star, the black hole whose image was captured in 2019, is incomparably larger. Its mass is 6.5 billion solar masses. Its Schwarzschild radius is approximately 19.3 billion kilometers. Its event horizon is wider than the entire solar system, out to Pluto and beyond. The shadow visible in the Event Horizon Telescope image is a region 38 billion kilometers across, silhouetted against the glow of matter falling toward it from tens of thousands of light-years away. On the other extreme, a black hole formed by the collapse of a star roughly 10 times the mass of the Sun has a Schwarzschild radius of approximately 30 kilometers, Its event horizon is smaller than most cities. It would fit inside the beltway of Washington, D.C. And yet, everything within that 60-kilometer sphere has been permanently removed from the causal structure of the universe. Light emitted anywhere inside it will never reach your eyes. Not because it is absorbed, not because it is scattered, but because the geometry of space-time inside that boundary does not contain a path that leads outward. There is no way out because the geometry itself has been closed. This is the nature of what gravity can do when it wins completely. Not just pull matter together, not just heat gas until it glows, but close off space-time. Create a region of the universe from which the rest of the universe is permanently, geometrically, mathematically inaccessible. Newton never imagined this. His gravity was a force, and forces could be overcome. Einstein's gravity is geometry, and geometry of the right kind cannot be escaped. It is not stronger than any available thrust. It is not a barrier that better technology could pierce. It is the shape of space-time. And the shape, inside the event horizon, points only inward. Chapter 12. The deepest question. There is a philosophical dimension to the event horizon that physics cannot resolve and that no observation will ever address directly. The event horizon is the only structure in the known universe that enforces a permanent, absolute separation between one region of space-time and another. Not a wall, not a barrier, not a medium that absorbs and re-emits. A geometric cut. A place where the causal structure of space-time is divided into two parts that can never communicate. If you were to fall into a black hole, you would, by the lights of general relativity, continue to exist for some time after crossing the horizon. You would continue to experience time. You would see the universe outside, blue-shifted, compressed into a shrinking circle above you as the geometry around you grew more extreme. You would not, from inside, be able to do anything with that information. You could not send it out. You could not warn anyone. You would know things that the rest of the universe could never know. The inside of the event horizon, the geometry of the approach to the singularity, the final moments before whatever the singularity does to matter. And all of it would stay with you. Not because you chose to keep it, because physics required you to. The event horizon is the universe's most complete secret keeper. Not out of malice, not out of design, but out of pure geometry. The most extreme consequence of the most precisely tested theory in the history of science. A structure that should not exist, that many brilliant physicists in the early 20th century refused to believe existed, that turned out to be not just real but common, a standard feature of every galaxy, a natural endpoint of every sufficiently massive star. We have imaged them, we have heard them collide, we have calculated their temperatures and their entropies, we have built a thermodynamics of their surfaces, we have derived the equation governing how they radiate away their mass over timescales longer than the age of the cosmos. We still do not know what happens to the information that falls in. We still do not know what the singularity is made of, or whether the word made even applies. We still do not know how to reconcile the view from outside, where the infalling matter appears to freeze and fade at the horizon forever, with the view from inside, where the crossing is smooth and the singularity is a feature of the future. We still do not know whether a firewall burns at the edge of the event horizon or whether the crossing is as gentle as general relativity predicts. These are not small gaps in an otherwise complete picture. They are chasms that run through the foundations of physics. They are places where our two most successful theories of nature, General relativity and quantum mechanics come into direct and irreconcilable conflict. And the event horizon is exactly where the conflict lives. Epilogue. The patient darkness. You can go outside tonight and look up. You will not see any black holes with your naked eye. They are black. The nearest stellar mass black holes are hundreds of light years away. The supermassive black hole at the center of the Milky Way is 26,000 light years away, hidden behind the dust and gas of the galactic plane. But you will be looking through a universe filled with them. In the Milky Way alone, estimates suggest hundreds of millions of stellar mass black holes, remnants of massive stars that burned bright and collapsed into silence over the last 10 billion years. Every large galaxy has a supermassive black hole at its center. The universe contains at least 1 trillion galaxies. The event horizons collectively enclose volumes of space-time that our minds cannot begin to process. And in every one of those enclosed volumes, the same physics holds, the same geometric perfection, the same silence, the same one-way membrane through which matter, light, and information travel in exactly one direction and from which nothing has ever returned, and from which, as far as current physics can guarantee, nothing ever will. What happens at the event horizon is not destruction. It is not violence. It is a boundary, a threshold defined by pure geometry, crossed in silence, experienced as nothing by the crossing observer, and experienced as an eternal frozen image by the watching universe outside. What happens at the event horizon is the quietest, most absolute, most mathematically perfect thing the universe does. The physics stops, not with a bang, not with a scream, but with the patient, absolute certainty of a geometry that points only one way, closes only one door, keeps only one secret. Forever.